Hello and welcome to the fourth lesson on binomial theorem. Before we take up some special and interesting problems, let us just quickly recall what binomial theorem is and how we are going to use a expansion 1 plus x raised to the power n in place of a plus b to the power n. So, starting with what is binomial theorem? Binomial theorem for positive integral index n states that a plus b raised to the power n expands to be nc0 a to the power n plus nc1 a to the power n minus 1 times b plus nc2 a to the power n minus 2 times b squared, and the general term tr plus 1 in the expansion given as ncr a to the power n minus r b to the power r plus the last term ends up as ncn b to the power n. That means, here we are expanding with the idea that the powers of a, which is the first term in the binomial, reduces by 1 in each successive term, and the power of b, which is our second term in the binomial, its powers increase by 1 in each successive term. And of course, NCR is nothing but n factorial by factorial of n minus r times r factorial. Now, in place of this, we are looking at expansion of 1 plus x whole to the power n. Then the expansion becomes a little more simplified, because our first term a is now 1. So, all powers of a will just get replaced by 1, and therefore, they are not going to be affecting the expansion. So, what does 1 plus x to the power n looks like? nc0 plus nc1 times x plus nc2 x squared, so on up to the general term, that is ncr x to the power r, and then the sum continues till the last term, which is the n plus 1th term, to be ncn x to the power n. Now, the advantage or something special about 1 plus x to the power n is that its general term tr plus 1 looks like ncr x to the power r. That means, the coefficient of tr plus 1, the binomial coefficient of tr plus 1, which is ncr, is also the coefficient of x to the power r. So, there is no other constant number which is contributing to the numerical coefficient of x to the power r. So, we say that the coefficient of x to the power r in the expansion of 1 plus x whole to the power n is NCR, and we also say it same as the coefficient of the r plus 1th term in the expansion of 1 plus x to the power n is NCR. So, they become one and the same, simply because there is no other constant number which is contributing to each term, and therefore, our problems will be framed around this idea, and here is our first one. The first problem says, in the expansion of 1 plus x raised to the power 10, the coefficients of 2r plus 1th term is equal to the coefficient of 4r plus 5th term. You have to find r. So, we are talking about the expansion of 1 plus x whole to the power 10. So, binomial is 1 plus x, and therefore, the coefficient of 2r plus 1th term will be the same as 10c 2r, right. That is what we are going to make use of. So, we knew and we followed as in the previous case, the coefficient of tr plus 1 in the expansion of 1 plus x to the power n was NCR. Therefore, coefficient of 2r plus 1th term in the expansion of 1 plus x raised to the power 10 will be 10c 2r. Similarly, the coefficient of 4r plus 5th term will be 10c 4r plus 4. these two quantities are given to be equal. So, from here I have to find R. Now, there was a result that we had talked about earlier in maybe permutation combinations, where we understood that if NCR is equal to NCS, then that may imply that either R is equal to S or R and S add up to be the same as N. So, this simple result and an observation helps us to say that 10C2R is equal to 10C 4R plus 4 if and only if. So, it is a two-way result. 2R is equal to 4R plus 4 or 2R plus 4R plus 4 must be equal to 10. So, solving for R from here, you get either R is negative 2 or R is 1, but then R in this reference cannot be negative, and therefore, if we reject R to be negative 2, we get our answer, that is a value of R to be 1, right. Now, this kind of a question is very popularly tested as a 1 marker, because it is based on a simple fact of knowing that NCR is equal to NCS if and only if either R is equal to S or R plus S is equal to N. Let us take our next question, which is definitely not a 1 marker. So, note it down and let us start thinking about. If in the expansion of 1 plus x whole to the power n, the fifth term is 4 times the fourth term and fourth term is 6 times the third term, then find the values of n and x. So, we are still talking about the expansion of 1 plus x raised to the power n, and you have to find n and x, two unknowns. To find two unknowns, you must have two conditions, and they are given to you in terms of how the terms are related to each other. So, if you start interpreting the given conditions and try to use some elimination method, you will reach the value of x and n. So, shall we start? Start by interpreting the first condition, which says that the fifth term is 4 times the fourth term, and also we are talking about 1 plus x to the power n. Therefore, the fifth term will be nothing but NC4 x to the power 4. 4 times the fourth term is nothing but NC3 x cubed. So, from here I get x to be equal to 4 times NC3 divided by NC4. If I rewrite the NC3 and NC4 in terms of factorial, there is definite simplification happening. N factorial will get cancelled. Between n minus 3 factorial and n minus 4 factorial, I expand the larger of the two, which is n minus 3 factorial, and I will end up with n minus 3 cancelling out, n minus 3 factorial cancelling out, and I am left with x to be same as 16 by n minus 3. Similarly, if I use the second condition, that is the fourth term is 6 times the third term, and then if I replace the value of each of these terms by NC3 x cube and NC2 x square, you will get x to be again simplified, and you get a condition which says x must be 18 by n minus 2. So, you have two values of x, but we are talking about the same x. So, from 1 and 2, I can equate the value of x, which gives me the value of n. So, solving 16 by n minus 3 equal to 18 by n minus 2, I get n to be 11. Once I have n as 11, use either equation 1 or 2 and you get value of x to be 2. So, if you look back at the problem, it was again interpreting the condition and also keeping in mind that we are talking about expansion of 1 plus x whole to the power n, in which the general term, that is TR plus 1, is nothing but NCR x to the power r. So, the task becomes much easier to handle. So, are you ready for our next problem? The problem says, in the expansion of 1 plus x to the power n, 3 successive coefficients are 462, 330 and 165. Find n. So, what do we mean by 3 successive coefficients in the expansion of 1 plus x to the power n? 3 successive coefficients will be the coefficients of 3 successive terms, right. So, you can assume those terms to be rth term, r plus 1th term, r plus 2th term, or you can start with rth term, r plus 1th term and r plus 2th, or r minus 1th term, rth term and r plus 1th term. You can't assume them to be specific term like 3rd, 4th and 5th, because we don't know anything about their position. But the best thing about such a problem is that we are looking at expansion of 1 plus x to the power n. So, we know that the coefficient of r plus 1th term will be nothing but NCR, and therefore, instead of starting the problem with the term itself, I can start with the assumption of what are the 3 successive coefficients. So, I start with assuming that the 3 successive coefficients are NCR minus 1, NCR and NCR plus 1. So, NCR minus 1 is the coefficient of TR, NCR is the coefficient of TR plus 1 and so on. Now, these are given to have the value 462, 330 and 165 respectively. So, let us replace each one of them with their values and see what we get. So, we know that NCR minus 1 is 462, NCR is 330, NCR plus 1 is 165. 3 conditions should be sufficient for us to work with and get the values of x, n and r as well, but we have to find only n and r. In this case, we are looking at again elimination between the 3 equations. So, if I start dividing the second equation by 1, or as in this case first by second, I get a condition between n and r by replacing each of these NCR and NCR minus 1 in terms of factorial. When I expand the larger of the 2 factorial, the expression simplifies and gives me a equation as r by n minus r plus 1 is equal to 7 by 5. What you have to keep in mind is that between n minus r plus 1 and n minus r factorial, n minus r plus 1 factorial is a larger one. So, you break down n minus r plus 1 factorial as n minus r plus 1 times n minus r factorial. So, that would get cancelled, and similarly between r and r minus 1 factorial, r factorial is the larger quantity. So, we start rewriting that and it simplifies. If I cross multiply, I get a linear equation in n and r. So, I have one condition between n and r. Can I find another one? Surely, I can always go back to the given conditions and I can now divide the second equation by third. So, when I divide the second equation by third, I again get NCR by NCR plus 1 is equal to 330 by 165. If I replace each of these in terms of the factorial as in the previous case, you end up with another linear equation which is same as 2n minus 3r minus 1 equal to 0. Now, solve fourth and the fifth equation for n and r. You get on solving n as 11. If the problem asks you also to find the position of these terms whose successive coefficients were given to you, then you can always put n equal to 11 and get the value of r and hence the position of the terms as well, right. So, we are looking at a problem where we are depending on the expansion of 1 plus x to the power n. We have another very special problem. It is there in your NCERT textbooks as well, and let us see what we can do with it. The third, fourth and fifth terms in the expansion of x plus a whole to the power n in descending powers of x are 84, 280, 560 respectively. You have to find x, a and n. So, now we are not talking about 1 plus x to the power n. We are talking about a plus x to the power n, and we are given that the expansion has to be in the descending powers of x. So, x is to be taken and is given to be the first term, a will be taken to be the second term. Starting with the general term of the expansion x plus a to the power n, we have NCR x to the power n minus r, a to the power r. So, if we rewrite the third term whose value is given to be 84, we get our first condition, which is NC2 x to the power n minus 2 a squared, T4 r is now 3, NC3 x to the power n minus 3 a cube is equal to 280. So, second condition, and the third condition is coming from knowing that the fifth term is 560. Fifth term will be NC4 x to the power n minus 4 a to the power 4. So, for fifth term r is 4. Now, from these three equations we have to solve for x, a and n. So, what I can do is I can start by dividing, simplifying. So, starting with second equation divided by first, I get NC3 x to the power n minus 3 a cube divided by NC2 x to the power n minus 2 a square equal to 280 by 84. Now, this will get simplified a whole lot, but to do that I must rewrite NC3 and NC2 in terms of factorials, club the powers of x and a, and of course 280 by 84 also simplifies to be 10 by 3. Again, using the idea that between n minus 3 factorial and n minus 2 factorial, n minus 2 is larger. So, I expand n minus 2 factorial and it would simplify the entire left hand side to be same as n minus 2 by 3 times a by x is equal to 10 by 3. From here, I write the value of a by x. A by x is same as 10 by n minus 2. Why have I separated the value of a by x? Well, it will become more meaningful if I start now dividing third equation by 2. So, dividing the third equation by the second equation, again simplifying NC4 and NC3, clubbing the powers of x and a, you will see that you will again get a by x. Therefore, a by x from here is 8 by n minus 3. So, we have a by x as 10 by n minus 2 and now a by x is 8 by n minus 3. So, if I equate the value of a by x from the fourth and the fifth equations that we have got, I will be able to solve for n. So, I have got now n as 7, but I still have to find a and x. At the best, right now we have a by x to be same as 8 by n minus 3 or 10 by n minus 2. Once I know that n is 7, I get a condition between a and x. So, a is 2 times of x. So, I have value of n, I have expression condition which relates a with x, but I have to find both x and a as well. So, what can one do? Go back and see what the condition to start with was. We were given that the third term is 84. Now, I know that n is 7, a is 2 times of x. So, if I replace n by 7 and replace a with 2x, I get an equation in x only. So, replacing n with 7, I now have 7c2, which simplifies, and the powers of x can be collected together. You end up simplifying a simple equation x to the power 7 equal to 1. So, now we have n as 7, a is 2 times x. To solve for x and a, we can always go back to our given condition, which said that the third term is equal to 84. So, if I go back to the equation nc2 x to the power n minus 2 a squared is equal to 84, and I put n as 7, a as 2 times of x, nc2 gets replaced with 7c2, simplifies to be 7 factorial by 2 factorial times 5 factorial, x to the power 5 into the square of 2x must be equal to 84. So, it becomes an equation now only in x. As I collect the powers of x and I simplify the constants, I end up with simply x to the power 7 is equal to 1, which gives me x is equal to 1. So, I have n, I have x, and a being 2 times x is equal to 2. Therefore, with the given conditions, we have been able to find n as 7, x as 1, a is equal to 2. So, the question was in terms of x plus a to the power n, the 3 specific terms were given. It is only algebraic simplification, but careful, right. So, you need to be very clear in your elimination process. We can easily reach the required answer. And so, in this lesson and in the previous lessons on binomial theorem, you have experienced different type of problems which can be solved using binomial theorem, and of course, how to prove binomial theorem using principle of mathematical induction. So, do take up some more exercises and see if you can master those and many more. All the best and see you later.